So, half-life. Okay. It's one of the things they talk about with nuclear stuff all the time. They describe its half-life, and what they're describing is a time. Half-life is a time. It's going to be in hours, a minutes, a seconds. And it's the time it takes for half of the atoms in the nuclide to decay. So when so you start off with, measure how much you got when you start, and you stop the watch when half of it is decayed. Now, nuclear decay is based on randomness. The motion of those particles inside the nucleus, if they randomly change, they randomly disintegrate. There's always a chance that any atom can disintegrate in any fraction of time, and it's completely random. You can't control it. But that leads to a bizarre thing. Because it's completely random, it makes it so the half-life doesn't depend on how much you have. So half-life is independent of how much you have. So if I start off with 100 grams, after one half-life I'll have 50 grams. If I start off with 50 grams, after one half-life I'll have 25 grams. Doesn't matter how much I start with. Okay, to show you how that give you an idea of how that randomness works. Okay, flipping coins is random, right? But if I took 32 people and had them flip a coin every minute, after the first minute, half of the people would be gone. Right? So they flip one coin a minute, comes up heads. On average, you'd expect half of those people to be gone after the first flip. Make sense? Okay. Next flip. How many would you expect to be gone? Well, half of what's left. Right? So after the first flip, I go from 32 to 16. Second flip, I go from 16 to 8. Right? So my rate slows down. I'm going half as fast the second time. But the amount of time stays the same. So half-life is an amount of time for half to disappear. Because it's random, it's constant. Because the process is random, the half-life is constant. And what it's measuring is stability. Because if it's got a long half-life, it doesn't fall apart very often. There's really a tiny, tiny chance that every individual atom is going to fall apart. Okay? If it's unstable, it's going to have a short half-life. Unstable means it falls apart easily. If it falls apart easily, it's going to have a short half-life. Okay? Now, they vary in time. Some are thousands of centuries. Uranium-238 on my chart here says uranium-238 has a half-life of 4.5 billion years. That if you wait 4.5 billion years, about half of the uranium-238 will have undergone a decay. So that means that we got about half the original uranium-238 on the planet. Because Earth is about 4.5 billion years old. Okay? Some of them have shorter ones, like 12.7 hours. Some of them are actually in microseconds. That as soon as you make it, it falls apart. Oh, by the way, that billion years is not the biggest number on here. There's 10 to the 12th, 10 to the 13th. That means, and that stuff, almost all of it is left. Because you haven't used up half of it yet. So, what this tells us, by measuring how fast it by measuring how much I have left, I can tell how long it's been. Okay? And that's the idea behind carbon dating. figure out how old something is, they measure how much carbon-14 is remaining. Talk more about that later, about how it works, how they know, how they get the time out of that. How do they know that papyrus is 2,100 years old? Okay. Okay, so we're going to use some calculations. We're going to calculate how much stuff. We're going to calculate how many half-lives. And we're going to calculate how much time it takes to get there. Those are the three things we can calculate. How much is left after so much time? How much time will it take to get to so much left? And how many half-lives will it take? Okay, so in one half-life, you'll have half the original material. Everybody agree? In two half-lives, you have a quarter. And you can just keep going like that, right? Now, because the function behind this is exponential, we're going to have to use a numerical method of solving these problems. Unless you know logarithms, then you can use the logarithms to solve them. But you're probably going to learn about those this year. So here's one of the places where you can use them. Okay. So we're going to make a table. And our table is going to have time, half-lives, and the amount of starting material. And the mistake people make most often, the first entry in time is 0. Time 0, where you started. First entry in half-lives is 0. You haven't gone any half-lives when you started. So it's bizarre that you have to start your table with zeros. You should start tables with 1. That's the first mistake people make often, is they start with 1 half-life and say, no. You haven't gone a half-life yet. You got to start off with 0. And so then in the next row, you're going to add 1 half-life. So if you're at 0, now you're at 1. And you're going to add that time. If the half-life was 5 seconds, I'm going to add 5 seconds. I'm now 5 seconds in. And I'm going to take my original starting material and cut that in half. That's going to be how much stuff I have left. And they can count that starting material in a whole bunch of ways. They can count it in grams. They can count it in the number of atoms. Then you go to the next row. Add another half-life. Half-life number 2. Add another amount of time. 5 more seconds makes 10. Take the original starting material and cut it in half. And just keep using this table until you get the answer to the question they asked. So you get the right number, gone the right number of half-lives, or you have the right amount of material remaining, or it's been the right amount of time. Any one of those. So we're just going to make a table and go until we have the answer to our question. So you're just going to fill out the table until you get the answer you need. So the table looks something like this. Oops, for some reason it's not writing the word time up here, so I'll have to. So you make a table. So let's say I started off with 64 grams. If I start off with 64 grams and my half-life is 10 seconds. When I started, I hadn't gone any half-lives. I hadn't gone any time, so I still had all 64 grams left. So the next line, next row, I go 1 half-life. How much stuff is going to be left? Half of 64. So that's 32. How much time will have gone by? Well, the half-life is 10 seconds, so 10 seconds will have gone by. So after 10 seconds, I wouldn't have 64 grams left. I'd have 32 grams of this stuff and 32 grams of whatever it turned into. Right? Because they don't disappear. They just turn into a different kind of atom. Everything's still there. It's just we're not counting them anymore because they're not the same kind of atom. Okay. So next line, how many half-lives? 2. How much remains? Half of 32 is 16. How much time has gone by? Well, I've gone another half-life, so I've gone another 10 seconds. So now we're 20 seconds. Pretty easy table to fill in. 3 half-lives, I'll have 8 grams. Here's where people make the mistake. People think, oh, I cut this in half, so I double that. No, 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 no. You're not doubling. You're adding 10. Okay? The amounts get cut in half, the times just keep adding up. See how you're tempted to put 40 there? Because you were. I was tempted to put 40. I cut this one in half, I double that one. No, that's not what you do. Cut this one in half, add the time to it. And so 4 would be 4 grams and 40 seconds. And is there any reason for me to keep going? Because those are the 2 places you're going to make mistakes. Not making those zeros, and somebody's going to put 40 seconds here. I know you're going to do it because I've read these a few times. Okay, I'm trying to talk you out of it. Hopefully, yeah.
So wouldn't it go on forever because you keep cutting it?
Yeah, keep cutting in half. So eventually it gets to the point where you can't detect it. Okay, that's really what happens. Is eventually it goes down. But so the stuff with a half-life of microseconds, it's all gone because technically you can keep dividing in half. But eventually you're going to get down to 1 atom. And that 1 atom in that half-life is going to have a 50% chance of falling apart. The next half-life is going to have another 50% chance. So eventually they will all go, okay? Because it's not a number line, it's a series of individual pieces. Okay. So, I mean, if you've got something that's got billions of years, it's not going to show up on your timetable very often because the Earth isn't that old. How do they know the Earth's that old? Keep throwing out these numbers like billions of years. How do they know that? So let's try some. The half-life of cobalt-60 is 5 years. If you have 12 grams of cobalt-60, how much do you have after 15 years? We have to make a column. Half-lives, amount, and time. When I started off, I had 12.0 grams, and I hadn't gone any half-lives, and I hadn't gone any time yet. So I'm going to keep going in time until I hit 15 years. Does that make sense? So after 1 half-life, how much would I have left? Not 6. 6.00. I had 3 sig figs when I started. I cut it exactly in half. I keep 3 sig figs in my answer. That's going to take 5 years. So after 2 half-lives, I will have 3.00 grams. And now I've gone another 5 years, so I'm at 10 years. Have I got the answer yet? Nope. I've gone 3 half-lives. I'm going to be down to 1.50 grams. And that's going to take 15 years. Oh, that's going to take 15 years. I will have 1.50 grams left after 15 years. Ta-da. Okay. This is called a numerical method. There's an equation behind this, but you just have difficulty solving it sometimes. So I can figure out how much is left after so much time. Or I can figure out how long it's been. I can use it as a clock. Americium-242 has a half-life of 6 hours. You started with 24 grams, and you now have 3 grams. How much time has passed? Okay, I still started 0 half-lives and 0 time. This time I started off with 24 grams. Okay, after 1 half-life, I will have 12 grams left, and that would have been 6 hours. 2 half-lives, 6.0 grams, 12 hours. Now, somebody might say, oh, Mr. Green, 12 has more sig figs. And it should, because I did not multiply by 2, I added 6. Okay, and 6 is about it's in the ones, I got to keep the number in the ones place. So I get another sig fig when I do this. Okay? Oh, sorry, didn't finish that. Because we don't have 3 grams left until we go to the 3rd half-life. That gives me 3.0 grams, and that's going to take, well, I double 12 and get 24, and then Mr. Green marks it wrong because we don't double 12, we add 6 to it. So it's 18 hours. And there were a few people who put 24 there before I said something. Told you, it's an easy trap to fall into. I want to do it all the time, so you got to stop and think about it. I'm adding time, I'm halving amounts. Okay. So there's an equation behind it. There it is. The mass remaining equals 1/2 to the n times the starting mass, where n is the number of half-lives. So if they tell me how long it's been, and I know how long the half-life is, I can figure out how many half-lives. Think about the last example, or sorry, the first example. You had 5 years was the half-life, and 15 years is what you wanted. So my time was 15 years. The half-life was 5 years. I've gone 3 half-lives. So if I've gone 3 half-lives, I want 1/8 of my starting material. That's 3 half-lives. That make sense? Okay, so that way you can find out the mass remaining if you know the time and the half-life. What if you wanted to solve for half-lives? Could you solve this for half-lives? Could you solve for n? You haven't learned how to solve for exponents yet. So that's why you're studying logarithms this year. It's because that's how you solve for those exponents. Okay? Because you never had to do that before, right? You never had to solve for the exponent. Yeah. Because we got the math this year. I know what you're going to learn. So, iodine 131 has a half-life of 8 days. If you have 8 grams of I-31 and 16 days pass, how much iodine 131 do you have left? Okay, so there's my starting point. I have no half-lives, no time, and I have 8 grams. So 1 half-life is going to cut that half into 4, and it's going to be 8 days. Not done yet. I want to go to 16 days. 2 half-lives will be 2 grams, and that would be 16 days. So they wanted 16 days. It's going to be 2 grams left. Now, equation, the mass remaining equals 1/2 to the n. Well, I got to figure out n. N is 16 days of time over 8 days of a half-life. It's 2. Times the starting amount. See, that gives you the same answer. Because 1/2 squared is 1/4, and 1/4 of 8 is 2. Okay? So it gives you the same answer, no matter which one you're doing, which way you do it. Okay, so we said they used this for carbon dating. Well, that changed. Oh, something happened here. Okay, well, so here's how you get carbon-14. Sorry. Calculating the age with half-life. So nitrogen in the atmosphere, that's what the life in the middle of atmosphere somehow changed while I was going one slide to the next. Okay. So nitrogen in the atmosphere gets bombarded by neutrons from space. Occasionally those neutrons hit the nucleus, and nitrogen gets changed to carbon-14. So this is not decay, this is a transmutation we read about, where something outside comes in and makes a different kind of atom by adding to it. So that means there's a constant amount of carbon-14 in the atmosphere. That's because the carbon-14 is decaying as soon as you make it. But you keep making more, so eventually you end up with a constant amount of carbon-14 because it's being made just as fast as it's falling apart. So you end up with a constant amount. So living things end up with that amount of carbon-14 as in their bodies. So you have the same amount of carbon-14 in your body that the air around you has, because that's where you get your carbon from. The air, because the plants get their carbon from the air. They take the CO2 and turn it into sugars. You eat the sugars, that's where you get your carbon. So your carbon matches the carbon in the atmosphere while you're alive. But when the thing dies, it stops taking in carbon-14. And but the carbon-14 in its body still falls apart. So your body is going to have less, the dead thing is going to have less carbon-14 than everything around it alive. And by how much is remaining, you'll know how long it's been, because we know the half-life of carbon-14 is 5,700 years. So if you know you're supposed to have so many grams of carbon-14 and you got that much less, you can figure out how long it's been in order to get there. Now, as long as it hits a perfect half-life, we can do any of them. But if it does, we got to use the equation, or actually, we can graph it. And this is what a decay graph looks like. It's an exponential function, okay? But it touches the axis eventually, but it's an exponential function. Because you can see that this is carbon-14, and if you have 50% at about 5,700 years, just short of 6,000, right? And then 5,700 times 2 is just over 11,000. That's when you'd have 25,000. Then you have 25%. So all I did was just connect the dots for each one of those. That make sense? So by measuring the amount remain, if you've got 70% of your original carbon-14, you know it's been about 3,000 years. Maybe 3,300 years. You just read it off the graph. If you know how much is left, you know how long it's been. That's what happened. Okay. Now there's limits to this. I mean, when I go from, I can see the difference between 70 and 72% here, right? It's readable on that graph. But what about the difference between 4 and 5? What happens when you get down here? Are you going to be able to tell those numbers with any certainty? The graph's not really going to help you, right? So carbon-14 doesn't work forever. It's only one of the things that can do that. Okay, we can use other isotopes. Okay. Okay, other isotopes. We can't let too much disappear if we want accurate answers. I can't get down in that 4 and 5% range. The closer I get to that 0% left, the more unsure I am of how long it's been. So different isotopes are used for dating just different age ranges. Because carbon-14 is only good up to about 50,000 years. It's about 9 half-lives is about as far as you can go. Because you're down under 2% remaining when you've gone 9 half-lives. And that line is really flat at 2%. But I keep throwing around numbers like, hey, the Earth is 4.5 billion years old. How do you know the Earth is 4.5 billion years old? Well, They use uranium. A couple kinds of uranium. Uranium-235 has a half-life of 704 million years. If you can go to 9 half-lives, that's 66.3 billion. That's older than the Earth. And uranium-238 has a half-life that's actually about the same as the age of the Earth. Its half-life is about the same age as the Earth. So right now we have about half of the original uranium-238 that was here when the Earth was formed.